Hello, this is Darren Pulsifer, Chief Solution Architect of Public Sector at Intel, and welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. On today's episode, Certifying Autonomous Flight with Luuk Van Dijk, CEO of Daedalean. Luuk, welcome to the show.
Thanks for having me.
Hey, Luuk, you're the CEO of Daedalean. Did I say it right?
Almost. I say Daedalean, but I accept any. I when I chose the name, I knew I was going to have to accept all the pronunciations that people can come up with.
So it's great talking to you. We talked just briefly before this, and I've learned about your company through a former Intel employee. Really fascinating stuff. But before we get into that, Luuk, tell us a little bit about yourself.
Okay. My name is Luuk Van Dijk. I'm a physicist by training, actually a theoretical physicist, but I bluffed my way through a career of programming computers. I moved from the Netherlands, where I was born and raised, to Zurich in Switzerland when Google opened an office there back in 2005. I worked for Google for quite a long time, programming computers. Then I had the good fortune, an amazing opportunity to work for SpaceX on the flight controls in Hawthorne, California, for almost a year and a half. Then, for various reasons that we need to go into, I returned to Switzerland, which is very nice and comfortable and an excellent place to raise kids. And a couple of things came together that made me decide to start this company. There were a couple of things from my past, having worked for Google, having worked for SpaceX, seeing that, you can do things the aerospace way, you can do things the internet way, and you can fuse them and do amazing things. But certification is really something that you should use to make your thing better rather than see it as a bureaucratic handicap. That was something I got from the episode. American style ambition was something that, you have there that you have less of here. And that you can do flying is an interesting problem space to be in. So these things came together, and that's what made me decide to start Daedalean in 2016. And our goal was to bring modern robotics and artificial intelligence and machine learning and computer vision and all these things to the world of certifiable flight control systems. And the general belief back in 2016 was that machine learning, nobody knows how that works. Therefore, it's fundamentally uncertifiable. And on the other hand, the culture from academia and getting stuff to work, or programming things for phones, is completely disjoint from how you program stuff for aircraft or for rockets, for that matter. So I thought it would be interesting to join that, to bridge these gaps, and to create a way to use these modern techniques in aircraft, which it's a solution for an actual interesting problems, namely how do you fly at scale without relying very deep in the control loop on the human. And so that's what we set out to do. And today we're about 100 people, mostly in Zurich. I poached one of your employees.
Yes, you did.
The one you just talked about, to be my head of business development in the United States. So we have, her name is Jemaya Bourdain, and she was supposed to be here with me, but she's currently developing business. She heads the Phoenix, Arizona office and deals with all our key accounts, of which there are many in the United States. And then we have a little data annotation office in Latvia, and the core of the engineering happens here in Zurich. And what we've built so far is visual-based systems that, just like the human eye, can see where you are, where you can fly, where others are flying that you shouldn't fly into, and where you can land, which are arguably the three most important things you do if you're a pilot on your own in visual conditions in an aircraft.
So do you?
Yes.
I mean, that was a lot to unpack.
Yes.
I got to unpack a little bit of that. So you're targeting primarily these autonomous flying, like air taxis in urban areas, and I would love to have that. I would.
Yes. And who wouldn't?
Right.
And they were definitely the inspiration to get started. So in 2016, there were a couple of companies in Germany and also in the United States that were, starting with these eVTOLs that were called electric vertical takeoff and landing for urban air mobility or local regional mobility. And what struck me was that electrification of the drivetrain would make everything a lot simpler. And things that are simpler are safer and cheaper, and generally better. And so the total number of aircraft that are built in the world in any given year currently is around 1,500. Sorry, 3,500. So there's almost nothing compared to 80 million cars. But if this urban air mobility takes off, you're going to have 50,000 Jobies or 100,000 Betas or EHangs flying around the world, which would massively change the way the aerospace industry is stacked. So I thought, there's an opportunity, because how are these people going to find people with a commercial pilot license? So that's what got me started. Since then, two things happened. First of all, the timelines that I guess everyone had for these urban air mobilities was, it should be flying by now.
Yeah, of course.
Um, and turns out that so that didn't quite happen. The other thing that happened was we saw that in existing aircraft, there is actually a lot of headroom and there's a lot of things to be done. Also, we learned through discussions with people very high up at relevant authorities that barging in and saying, "Okay, we're going to take out the human, put in this computer here, trust us, it's safe." It's not a recipe for success. We knew that. You have to actually certify it. But they gave us the very important hint that we should be a good co-pilot before we try to be a good pilot, and that actually made us rethink our whole marketing approach. So, with respect to these eVTOLs, that was definitely the target we were going for. I guess this is a general theme in aerospace. The timelines are so long that things are only started by people who didn't get the memo. It was hard. I'm guilty. So I thought it would be done by now. These things would be flying. But that doesn't undercut the fundamental assumption that there's a viable business case here by solving these problems. Some of these eVTOLs definitely gonna happen, and they will need this because in current instrument flight rules, you can have one air taxi over London, and then everybody else stay the hell out of the airspace, because the air taxi is there, everybody's there. So if you want to fly 100 of these things over London or Paris or New York, you're going to have to do something different than flying in instrument rules. If you fly in visual rules, you get to maybe a couple more, but then the responsibility to not fly into each other is on board, and so you have to have a system that flies much better than humans to keep all these things apart. You need to introduce some vehicle-to-vehicle communication, but you can't really rely on a central system that solves it for everyone, because the rules of the air today allow people just to fly there. And these rules are set down in international treaties that change on the timescale of years. So one of our basic ingredients was you have to fly like a human between humans in a system that's designed, from 120 years ago around humans. So the humans actually very deep in the control loop holding a stick. And in most aircraft today, if you let go of the stick, eventually you will die, right? So the autopilot does a trivial amount of automation in cruise, but for almost all aircraft, you have to disengage that and do the landing by hand. There's
To
no
land, right?
helicopter. Yeah. For example, to land. And then there's a rule which in the United States is called Part 91.113, which says that even if you're flying instrument rules or visual flight rules, doesn't matter. If the conditions are visual, other people might be flying on visual rules, and that means it's your responsibility to look out the window to not fly into them. So there's no instrument today that can do the looking out the window. So it's actually on visual. It's in the law, and these things change very slowly. And there's a good reason that they are the way they are. So there's a bad reason, which is the legacy, but the good reason is, well, it works, and visual information is the highest density of information around us. It's not an accident that we have eyes that are sensitive to the spectrum.
Right.
So you want to build systems that can fly like a human, evaluating that information and fusing it all. This is another thing that is in aircraft today very much not the case. Every instrument is by itself clamoring for the attention of a pilot who has the job of fusing it all into one coherent picture of the situation. And this is on purpose, because not all the instruments are equally reliable, and you have to make some judgment calls. Say, I'm not trusting this GPS because I look outside and I can still see that I'm following this coastline. So somebody must have been messing with my GPS. GPS generally, it's a world miracle that the thing exists. It's not actually safe enough to conduct flight operations on. For example, you're not supposed to land on GPS. I mean, people do it, but you're really not supposed to. So the next thing you have to do is certify that, because in the air, nothing goes in an airplane without the FAA signing off on it.
And now, is a quick question on that, because does the FAA kind of control all the airspace throughout the world?
No, but
I know it doesn't, but I mean, but if I get an FAA approval on something, does everyone else kind of say, well, if you got FAA, it's good enough?
well, so
I don't know.
it's not that simple. But between the FAA and EASA, if the systems get certified,
Then you're in good shape.
then you're in a good start to the rest of the world will probably recognize or copy it. So there's different kinds of certification. This is about the instruments and the equipment. The other crucial thing is the right to operate in a certain way. So I have this airline. I fly from here to there doing this kind of operations. I do search and rescue, or I have this commercial what do you call it? Just transporting people to holidays, or I have cargo transports or organs, or that particular type of operation is also subject to certification. And there, the FAA is rules FAA land, also known as the United States of America.
Yeah.
And EASA rules EASA land, also known as the European Union and some nearby things. And so these are two aspects that you have to both have and bring. So if you have those two, then you have a good start.
So just real quick, because when you were talking, I was thinking this sounds a lot like the problems that we're having with autonomous vehicles and certification. And I need visual. Would you say a lot of the technical and political or certification issues are very similar to autonomous vehicles?
In some ways, yes, in some ways not. So we're really in a different corner of the design space. So first of all, driving is very unregulated, compared to the airspace.
Compared to that's
And the other thing is that if you drive and your robot doesn't know what to do anymore, your robot can try to gently apply
pull
the
over
brake,
and stop. Yeah,
flash the red light and say, I don't know what we're doing anymore. Let me stop.
you can't do that in an airplane.
No, it's called landing, and it's already the hardest thing. So if your computer doesn't know how to land anymore, you have quite a big problem. So and from remember, I'm a physicist. From a physics point of view, apart from the half mv squared component of your energy, you have the m times g times the height component of the energy, which is the thing that really kills you.
That's what killed you. Yeah, falling out of the sky.
And so with that, the barrier to try out new things, put new things in, is really far more rigorous than in automotive. In automotive, you have these certification levels for safety systems that goes to ISIL level D, which is the highest. So ISIL A, B, C, D. In aerospace, it's called DAL, the design assurance level, which goes from E, meaning it's cabin light, has no safety impact, D, C, B, A. So A is the highest. And one of the things your ex-colleague, analyzed in her time at Intel is that this ISIL D, this highest level, is roughly the same amount of work as DAL C. And to get to DAL A is twice more work.
Wow.
Twice bigger stack of paper with evidence that it actually works as advertised. So it's far more rigorous. And one of the consequences is that the systems that are allowed to do these kind of things are really simple, and it's technology of the 1980s and 90s, and they can do it super reliable, but it's also fairly simple stuff, and it requires a human to switch it on and off if it doesn't work, and it's deliberately not integrated, and it comes with all kinds of. So there's a massive barrier to get into that space, but the robotic problem is actually much simpler. So driving is a much harder problem than flying, because in driving you have this super complex environment where you have to understand the difference between a rock and a dog and a traffic sign and a bicycle that actually goes this way or one
Yeah,
that's
when you're
mounted on the
flying,
back
you
of the car.
just avoid
Right.
things, right?
Right.
Just
If you
don't
can
hit
see
something.
it, do not fly into it
Yeah.
unless you're really sure that you want to land on it. So that's a problem. And this is one of the things I already realized back when I started the company. So that's the size of problem that you can hope to solve with a fairly small team, right? So these cars, that was, in 2016, already more than a decade on the way since the DARPA challenge was won
Right.
by Sebastian Thrun. Um, uh, so you're going to need hundreds of millions of dollars and insanely big teams, and you're going to have this big shakeout between big companies trying to do this, and then even then there's going to be a valley of overpromises and a trough of the chef of
Despair.
dreams, yeah, and all that. So we have a small version of that too, but the general premise has remained intact. That flying, we can actually do simple things. And so one of the insights that came with these comments from people high up in the FAA, be a good co-pilot first, is also made me realize that if you come in with, okay, I'm going to take the human out, put this autopilot in, then you immediately have the uphill battle to fight. Oh, but is that safe enough? Whereas there are millions of pilots worldwide that have to fly single pilot operations. Poor them. What if we gave all these pilots an extra
An
co-pilot?
extra
You know,
co-pilot.
now we have a clear safety case where we can start by adding immediate safety, also some cost, but we'll work on that separately. So once we have this co-pilot rolled out, we can now do things that previously required dual pilot operations. Maybe we can do some of them with a pilot and an electric co-pilot, and then maybe in the course of hundreds of thousands of flight hours, we can gather the evidence that it's actually better if the electric co-pilot does the landing and the takeoff, because he tends to fly into fewer masts. Common thing with helicopters is flying into a mast that you just saw, you just forgot about it.
Yeah.
So things like that, and then we can say, okay, we can move to the phase where it's better if the human doesn't touch anything, and here's the evidence to do so. And so these are battles that will have to be fought on actual data and things that are true, and not on pipe dreams. So with respect to that, I've had to tell my investors, listen, in the course of the years, we've come to the understanding that we're not going to be done in 2021, but definitely 2028. I'm kidding. I'm kidding. So we are not in a hurry to do things wrong, and you have to do this carefully. So anyone who promises you beyond visual line of sight full autonomy, for arbitrary operations next year, good luck. The technology may be in principle there, but the evidence that is
But the evidence,
acceptable
right, to get
is
certification.
not. And that's just the autonomous flying part. So for many of these new airframes, you also have you have new propulsion, you have new structures, you have new types of operations. Everything is new. So
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 they
it
have
took a
to get
while.
certified independent, right?
Right, right. So you have to first have your airframe certified, to do piloted operations. There are some that want to go to autonomy directly, but then they also say, okay, which is also going to take us longer to get started. Um, so in the meantime, we think we have a valid business case with existing aircraft, both rotorcraft and smaller aircraft. Not the big part that's called Part 25, the big airliners. They're not actually that broken. So they're expensive, but they're super safe. There was a
Yeah.
year recently where there were zero crashes worldwide of any of these, and then the next one was the big disaster, but that was a common cause upstream that we shall not discuss.
Yeah.
But so that is it. That's not the most broken, and it's not the most urgent to fix. But anything that's smaller, smaller than 19 seats, um, all the helicopters, the probability to die per hour is roughly the same as riding a motorcycle,
Oh,
which for some people is acceptable. It's
for
a
others,
trade-off.
it's not.
There's a lot of headroom for safety and also for scaling the operations. Yeah, so that's a very interesting field to be in.
So Luke, a quick question, because the things that you're learning around getting this certification for autonomous, right? Because now we have AIs and machine learning that are starting to infiltrate all the work that we do.
Right.
like Chat GPT is a great example, right? That shaking the world. And can I
Yeah.
take any of the learnings that you guys have learned on how to certify autonomy for
Mhm.
aircraft? Can I take some of those learnings and apply them into other fields?
Um,
Do you think there's
Perhaps
some?
yes. I need to think about that. But first, we need to distinguish autonomy and this AI thing. So
Okay.
first of all, AI is of course a marketing term. It means
Yes,
anything
of
we don't
course.
quite know how to do yet. And, but so what we do is machine learning, and the reason we do machine learning is that's the only way to solve a problem like, is there an aircraft in this picture, or where in this picture is the runway, just from pixels. The only way to currently solve that is by using machine learning. So it's a means and not an end. Then these are building blocks you need to get to the types of operations you might want to do without pilots. So if that's your end goal, you're bumped into this. We can already do things that are not fully autonomous but still add value, because there's no other instrument on board that can look outside the window and say, "Ha, there's a runway," right?
Right.
There's so that's on the AI versus
Yeah. So
autonomy
so
side.
on
Oh,
autonomy. Yeah. Yeah.
learnings. Yes. So actually, a large part of what we do as a company, which we haven't talked about in the last half hour yet, is so first you need to make it work, right? Then you need to provide the evidence that it works to get it certified. What we had to do, we also had to develop the theory of how to produce the evidence that it works for a machine learning system. And that's actually very interesting because with these normal, traditional, simple avionics systems, um, uh, they work or not, and you can test it, and they work. They take a couple of bits of information out of the environment and manipulate a couple of bits. Even an engine controller for a turbine engine is relatively, it measures a couple of variables and it controls a couple of variables, and it does it very reliably. And you can test that, and it's not trivial to get it right, and it's easy to get it wrong, but we know how to do that. So now you come in with a camera as a sensor. Now I have 12 megapixels, and all these 12 megapixels can have a value between 0 and 255. So the input space is ginormous,
It's
and
huge. Yeah.
what kind of statement do you want to make about it works? Even the input space itself is too large to make such a statement, and that's for a reason. If you could easily say this is the crisp boundary between something that works and doesn't work, you probably didn't need machine learning. So you need machine learning to begin with, because the problem nature is such that you need something that can deal with the inherent uncertainty that is the problem. So what we did is we went to EASA first, that's the European version of the FAA, and we proposed a method, basically a framework to think about it. And then they said, that's very timely because we were just scratching our head what to do next. And so, come in. And we did two projects with them called the Innovation Partnership Projects, in which we paid EASA for their consultancy, but they added some consultants for free because the topic interested them selves. So a consequence of that was that we owned the outcome of that, but then we wanted the world to stop thinking that it was impossible to certify these things. So we published these reports, or the bulk of it, and then the FAA was interested and wanted to actually see, if that would stick, if the rubber hit the runway, the tarmac. And so we were invited to do a project with the FAA this was in 2021, and that report also came out because American taxpayer money, well spent, entirely public. And what we did there is we looked at the visual landing guidance, and in these three reports, what we developed was the theory of how to argue that a machine learning component is safe, which is slightly different than normal hardware and software. So we have the system that takes in a camera, and then there's a small component in there that tries to draw a box around an aircraft in the air. And it should be, which is really hard. And also for humans, so first of all, humans miss most of them because they don't actually see that much. But even though, if I can show you the image and you go, is that an aircraft? I'm not sure, it could be a cloud. And so you have to make a system that tries to make a judgment call, and then you have to guarantee that that system works well enough. So first you have to establish what is well enough, and we want to be able to see 95% of all traffic that comes within this distance. Okay, good. So we have that system requirement. Now, suppose we make a machine learning component that gets it right 90% of the time. then you have to do two things. You have to first make sure that that 90% of the time is actually good enough in the context of the bigger system. So
Right.
fortunately, we don't have just one picture to go on. Also, when you land, it's not like you look out the window once, close your eyes, and then
Close your
steer
eyes.
there. So
Right.
so so there's some inherent design freedom you have in making the system such that this 90% actually multiplies to something large enough, um, or that technically that 1 minus 90% multiplies to something large enough that it's
Right.
unlikely that you'll miss the runway, or that I'm not seeing the runway, let's not land here, let's defer to a higher level system. So that's one. And then the other thing that you have to do is you have to guarantee that this 90% actually holds when you go out and fly. So you train your system in the lab and you evaluate and you test it. You say, okay, this is acceptable. I have my system requirements which say that this is good enough. Now I go out and suddenly, the sun is from the east instead of from the west, and my system completely falls apart because I never thought to test with the sun coming from there. So how do you guarantee that the thing actually still keeps working when you go out into the wild? And that turns out to be dependent on how you treat your data. So in machine learning, instead of locking some engineers in a room with chocolate and coffee and requirements and waiting until they produce some code that works, you have a computer program called the machine learning algorithm, exploiting the design space of what's called the model, which is not a computer program. And when you've come to an acceptable model, you go and deploy it in the field. And that's driven by the data. So what you need for that is that the data that you use to evaluate your performance on is actually representative of the data you have out in the field, which is, it sounds trivial and obvious, but it's actually a massive shift from, how things were, how you could do things in the more uh,
Traditional way.
traditional system.
Yeah.
Now, you still need those traditional methods because this machine learned thing runs in software that runs on hardware. So this hardware still has to be certified. This software still has to be certified. But there's an extra thing you have to do. You have to certify that the emergent behavior of this neural network or whatever machine learning thing you did is adequate to solve the problem that you are trying to solve. So that's a whole thing that we developed with EASA and the FAA, and that we're now test driving with a partner. They're called Everdyne, based in Florida, and they're making for us the box and the camera, and we make the software. And we're applying for what's called an STC, Supplemental Type Certificate, under the FAA with concurrent validation by EASA. And so the software and the hardware will be ready pretty soon, and then there might be some more months before we're done presenting the safety argument to the FAA and EASA, and then we hope to be the first system in the world that has an SDC to design assurance level C, this is DAL C, which is not trivial for a machine learning component. And it's specifically for the application of traffic detection for human pilot assistance. So it's not immediately, the most ambitious fully autonomous flying. Here's a whole system that does
No,
everything.
but you're
This is
taking it step by step, which I
right.
understand.
And it will be a beachhead into certifiable machine learning systems. So once we show that this is possible and that we've covered the gaps, we have a system that has a clear safety benefit, right? It should actually work because if it beeps all the time and there's no aircraft there,
And that's
it's
yeah.
actually dangerous. If you give the pilot a false sense of safety, it's actually also super dangerous. So we're going to have a system that actually meets a non-trivial safety bar, and that we use the method to assure that the data was treated correctly.
Yeah, do you think I can use that same method in other machine learning systems? Like, for example, a forklift in
Right.
a factory, right?
I I would I would think yes. So now we've come to actually answer the question that you asked me 10 minutes ago. Is
Yeah.
this reusable somewhere else? So this method of assuring based on the data, so it's a combination of the data assurance guarantees that your machine learning component worked, and your architectural mitigation makes sure that the finite failure probability actually adds up to something reasonable at the system level. Those two things are, I think, generally applicable and could serve elsewhere. But yes,
So yeah, so can someone that's in this field, right? I mean, you don't want to capture the whole machine learning certification field. That's just
no,
massive.
yes.
where can they get more information on following the same approach? Because it sounds like a very well thought out, methodical approach that I would want to use.
Um,
Do you guys have a white paper? Do you have anything?
so we have some blog posts and white papers on our website, ddln.ai, so that you don't have to remember where all the vowels go, where we refer to some more things. So we tend to focus on aerospace because it's a big enough problem and it's
Right.
a large enough hurdle. So the temptation to spread out either into uncertified systems or into other domains is always high, but we've managed to keep a relative tight focus on manned flight. And yeah.
No,
Um,
the reason I'm asking is a lot of my customers and my listeners,
uh,
they're they're dealing with machine learning and AI techniques now,
right,
and they're trying to say, can I trust this?
right.
Does it need to be
Uh,
certified? What are the
well,
best methods? Right?
right. So for this particular application, and we've tried this out particularly on image processing, so convolutional neural network that recognizes things in images. That's what we're focused on. Things probably change if you're talking about language processing. So this whole
Right.
chat GPT that you mentioned earlier, so it's a massive accomplishment, but it's full of garbage. So in my opinion, it's so people used to think one of the applications of AI is try to understand more what human intelligence is like. And when I look at these chat GPT examples, I'm not sure about human intelligence, but I have a great model for human stupidity, which is so you mindlessly ramble and repeat stuff that you read before, without any creative thought or insight,
Yeah,
and it
exactly.
looks plausible, but it's the kind of statement you expect from the extremes on the political spectrum. And there's nobody. The Chat GPT does not go, well, I hear myself say this, but now I hear myself say this. Doesn't sound right. What irks me here? So
I
it's
actually I I actually interviewed Chat GPT on the podcast
oh, okay.
and asked it
And
about ethics and bias and things. And
yeah,
you're right. It was just regurgitating the things that it
right.
had
So that's
that it
actually
had said.
dangerous if people don't realize how unreliable it is. So I'm sure it's a great tool and it can be good to great use. But so 20 years ago, remember I told you I worked at Google. So finding things on the internet was hooray, it was
Oh
revolutionary. I
yeah,
can
yeah,
find all these
yeah.
things. With a little footnote, that we find it doesn't mean it's true, right? So you can find some things on the internet which
Wait,
are not.
wait,
So it's the
wait,
same
wait
with
just
this.
a second, Luke.
Yeah, nobody told
My
you.
kids
Yeah.
think that Google or Alexa knows everything.
Well, we did our best, I think, on behalf of my former colleagues,
Yeah.
but there are some risks associated with it. So now you have this great tool that can, and it's a UI tool that can be a great interface to a document search system. But the crap that comes up, it's
Garbage in, garbage
people.
out, right?
No, it's more subtle.
Oh.
It because it looks you don't see it's garbage, right?
Yeah,
So
no,
that's
it
actually
look
hard. And
yeah,
so
they
to
put
to
lipstick
make
on it for sure.
yeah, to put any kind of guarantee on it, is going to take some serious research, and it's going to boil down to the quality of the data. So if you feed it opinions, you have the true fact that that was somebody's opinion, but that doesn't make it true. So that's a subtlety that I don't know how that's modeled in the generative transformer topology, but it might be a detail that the
Oh.
system's not actually deal with. But who knows? So it's going to require someone to sit down and think about, what does it mean to certify? So that was actually our opening offer to EASA. People think it's not certifiable, but certifiable means to provide certainty, right? That's I think that's what it literally means. So why don't we go over all the sources of uncertainty and try to put bounds on them? How can we limit the uncertainty? And sometimes uncertainty is actually your friend. So if you have a physics background or you had some thermodynamics, you know that the law of large numbers and the central limit theorem can actually be your friend and can help things. So Sebastian Thrun, who won this DARPA competition that basically jump started the whole self-driving movement. He wrote a very good book about robots. And the introduction, he spells out that in the world is full of uncertainty. So if you want to make robots that operate in the real world, you have to build systems that can deal with this uncertainty.
Uncertainty,
And
yeah.
this is exactly where the friction with aerospace was, because in aerospace, we don't want any uncertainty. If it's uncertain, it's illegal. So you have all these systems that do very certain things, and then all the uncertainty is delegated to the human pilot who sits there making judgment calls. So if you just build an extra instrument along the same lines, you have one more instrument that clamors for attention, and the pilot has to make a call. So we start from the other side. If you want to deal with this uncertainty, first of all, we're going to fuse all the sensors. We're going to get every bit of information we can get, and then we build algorithms that trust nothing and try to sort out what's our state in the world. And if you start designing from that side, then you're in this machine learning territory. So then you have to say, is that spot certain enough to be an aircraft that I want to make an evasive maneuver, or am I going to, make judgment calls and not do that? And so if you start designing it with that goal, then you naturally arrive at, okay, now I have to prove that this is good enough. And then you're closer to certification of people as a qualified pilot, which you do by, you test them out a bit, and then you poke and you prove, and you trust them, then hard mathematical proof. So I think that's really what we added to the discussion.
Well, hey, Luuk, this has been fascinating. A whole new area for me is autonomous flight. I don't know anything about it. You've educated me quite a bit. And machine learning, I know a lot of my listeners are in the throes of this right now, because whether we like ChatGPT or not, it has raised awareness and increased the possibilities. Where can we go?
And it's not a matter of liking or not liking. It's the thing is there now.
It's causing people to really think more about machine learning and AI. So,
which is what the PC did in the 1980s. Now we have unlimited brain capacity on our desk. It's going to change everything. Look, a mouse.
It changed everything.
It did. And then the internet changed everything. And now some of these things will change everything again. But probably not quite in the way we expect, but probably in the way that we don't expect. So
it'll be an interesting time. Hey, thanks again, Luuk. I appreciate the time.
Anytime, and talk to you again sometime.
Thank you for listening to Embracing Digital Transformation today. If you enjoyed our podcast, give it 5 stars on your favorite podcasting site or YouTube channel. You can find out more information about Embracing Digital Transformation at embracingdigital.org. Until next time, go out and do something wonderful.